And Satyam, the floor is yours.
Hello everyone. I thank Argadeep for the introduction and the Indus Group for giving me the opportunity to present my work. So today I'm going to be talking about data constrained MHD simulations of solar flares. I hope I'm audible, Argadeep. Can you just please confirm once again?
Yes, you are audible, but the black bars appear on the screen once again.
It is
Yeah,
gone
it's
now.
gone now. Yeah, carry on.
Okay, so the general understanding is that solar flares are caused by magnetic reconnection, and in these events, a lot of energy gets released, which is attributed to the stored magnetic energy in the magnetic field. Also, it is now quite well known that during reconnection, field lines change their connectivity. But apart from these two aspects of reconnection, there is something else which is quite fundamental to reconnection and magnetized plasmas, such as which is present in the which is present on the sun. So I'll keep that something else which is very fundamental as a mystery up until the right point in my presentation where I can discuss it. So the overall objective of my PhD work and the focus of this talk is to explore these aspects of reconnection, including changes in energy, field line connections, and this something else, and using database or data constrained MHD simulations of solar flares. So I would like to start with an introduction to the subject. So on the left, solar flare up shown, which is generally characterized as a localized brightening. And it is known that magnetic energy gets released as heat, particle acceleration, and kinetic energy of the plasma by the process of reconnection. So the idea is how does reconnection occurs? So for that, the standard way of describing it is to use the magnetic induction equation of magnetohydrodynamics, which tells us how the magnetic field is evolving with time. So the equation is shown on the top, where the first term on the right hand side is for the advection of magnetic field with the plasma flow, and the second term corresponds to the diffusion of magnetic field. And standardly, if we take the ratio of these two terms, a dimensionless number is obtained, which is known as magnetic Reynolds number. So there are two limits of this number. One is if when it is much larger than one. So in that limit, advection dominates over diffusion, and we can drop the second term. So then the equation that we obtain is del B by del T equals curl of V cross P. And in using typical parameters of solar corona, Rm is estimated to be around 10 to the power 12. So this limit is particularly called ideal MHD limit. And what is important about this limit is that at such large scale, such large length scales, magnetic field lines and plasma parcels are tied together, which is also known as the Alfvén's flux freezing condition. So the basic idea is that if two plasma parcels are attached to a magnetic field line, which is shown on the left figure at time t1, and the field line deforms in certain way or in any arbitrary way, so those plasma parcels will always remain attached to that particular field line. But in the second limit of this, Rm is typically considered to be less than or equal to 1. Then in that case, diffusion term is considered to be dominant over advection, and the equation reduces to del B by del T equals to eta del square B. So when does this limit becomes important? Is at a small length scales, basically because when we reduce length in the numerator part, Rm reduces. So at a small length scales, diffusion is dominant. And this dominance at a small length scales is what sets the stage for magnetic reconnection. So the essential idea can be picturized from the right hand side figure. So which shows that two plasma parcels are attached to a field line L. And if this field line passes through a diffusion region, so this diffusion region at a small length scales, which is a localized region, then after that, one of the plasma parcels A is attached to line L1 while B is attached to L2. So initially they were connected to the same line, but now they are connected to different line, which is essentially what is defined as the general definition of magnetic reconnection. Also, there is another important fact that if we use Ampere's law, which is curl of B equals to mu naught J, so an order of estimate of the left-hand side part gives magnetic field divided by length scale. So at a small length scales, particularly where diffusion is dominant and reconnection can occur. So when length scale is small, current density is large. Therefore, the heating term, particularly eta j square, which is ohmic dissipation, becomes finite. So which gives rise to the heat generated during the reconnection process or these eruptive events, solar flares and CMEs that we observe. So this is the basis of how reconnection can occur, and then there are certain other important aspects. The first on the top left shows the general 2D reconnection picture, which most of us are familiar with. So this two-dimensional reconnection is generally occurs at an X point geometry. So what happens here is that a field line AB contains a plasma parcel and another field line CD contains a plasma parcel, and both are anti-parallel. So if they are brought closer towards the diffusion region, they break and rejoin. So the new field lines are moving in the y direction, represented by the field line AC and the field line BD. So, but I find it important to stress the fact that this same definition of reconnection, the breaking of field line and joining of field line, does not carry over to the three-dimensional picture. In three-dimensional reconnection is completely different. So in 3D reconnection, what happens is that if we have again two field lines AB and CD, so if they enter into the diffusion region, they break into four parts. So if we consider one of those parts, say if we consider a part which is traced from the foot point A, so then these field lines are set to flip through the diffusion region. So at one end of the field line, which is shown here, the velocity of the field line is equal to the plasma flow. But at the other end of the diffusion region and within the diffusion region, the velocity of the field lines is not equal to the plasma flow. So there is a sudden flip in the magnetic field and there is no perfect breaking and rejoining, which is encountered in 2D reconnection. So this characteristic that field line, the velocity of field lines is not same as the plasma flow, can be used to identify reconnection in the simulations also. Then there are certain preferential magnetic configurations where reconnection occurs. In three dimensions, the first one is the 3D null point. So null point is basically a location where all the components of the magnetic field is zero. And if one does a linear analysis about this location, then a configuration can be obtained. So in this particular configuration, which is shown here, so there are two sets of field lines. One is red and one is yellow. And these field lines are divided into two parts. One is called the spine and one is called the fan surface. So basically spine is this very narrow set of field lines which are bunched together on the top and the bottom, which is shown in the yellow. And as they approach towards the null point, which is located at the center, these field lines diverge out and form a surface kind of thing. So, and between these two surfaces, the one between the red and the yellow, there is a discontinuity. And if we extend this concept of the 3D null to, so a typical type of null which is encountered in the solar corona is the dome-shaped null point configuration. So basically what one has to do is close the entire fan surface on the photosphere so that the fan surface forms a dome kind of structure. This is often observed, seen in observations and yes. Apart from the magnetic null point, there are two other characteristic magnetic configurations which have received quite attention in the recent years. One is the QSL. So a QSL is based. So quasi-separated layers can be understood from this figure, where this sigma shows a surface on the left and right hand side. So on the left hand side there is a circle, and the two field lines are shown whose foot points are located at the end of the diameter of this circle. So this circle is constructed so that the radius of this particular circle is 1, and so that we can say that these foot points are 2 units apart. So, and if this field line configuration maps in such a way that the distance between these two foot points increases, and on the other sigma surface, these field lines are shown. So, and one can see that the distance between these two foot points has increased. So if we do not go into the mathematical description, so this increase in the separation between the two foot points is what is the essential characteristic to define a QSL. So if to characterize this QSL, a parameter called squashing degree is calculated. So for circle, this is always turns out to be 2. And for this ellipse kind of shape, the values calculated had to be 8.125. So it basically, the larger value tells us how much the field separation has increased, thus how much the separation between the foot points has increased. So in the case of null point where there is a true discontinuity, the Q value will theoretically tend to infinity because there is a true discontinuity. So QSL is kind of a weakened version of that discontinuity, where discontinuity is reduced to strong gradients in the magnetic field. So that separation is not too high, but limited. Then an extension of this QSL concept is called an HFT. So here again, in this right-hand side figure, a QSL kind of drawing is shown where a foot point is, where two foot points, where the foot points of two field lines at A are very close at this particular point, but then they diverge. One of them goes to C and one of them goes to B. So the same can be seen in this HFT figure also. The foot pointers A, B, and C are shown here. So if we consider a similar QSL, another one, which is starting from this particular location, then their intersection gives the HFT. And the HFT gives a 3D analog of the X point in 2D. So in HFT, it becomes a X-type region basically. So these are the essential configurations or the preferential configurations where reconnection occurs in 3 dimensions. So if we want to study magnetic field and magnetic reconnection, then we need to have information about the magnetic field in solar atmosphere. But as we all know that most of the routine measurements are restricted to the photospheric surface. So then we need some kind of modeling to construct the three-dimensional magnetic field. So that technique is referred to as magnetic field extrapolation, and is that and standardly the extrapolation models are divided into two categories. One is called the force-free category, and the second is called the non-force-free category. And the standard description of force-free follows from the momentum balance equation of MHD. So the equation on the left-hand side shows that acceleration term multiplied by mass is equal to the forcing terms on the right-hand side, which is the Lorentz force J cross B, pressure gradient, and gravitational force. So if we do a if we make this equation dimensionless with proper normalization and look for typical values in the solar corona, then that gives us the force free approximation in which the left hand side is 0 and the right hand side terms grad p and rho g are rendered negligible in comparison to j cross b. So which gives us essentially j cross b equal to 0, hence it is called force free approximation. So typically there are three solutions of this equation. One is the j equal to 0, which is a trivial solution, and it is called potential field. The second is j equals to alpha b, where alpha is some scalar function but constant, and it's called a linear force free field. And the last is the j equals to alpha rb, where alpha is a scalar function but dependent on the position vector. So this is called the nonlinear force free field. And in contemporary literature, nonlinear force free field is often used to model the magnetic field in active regions. So in my work, I have used this NLFFF code developed by Wiegelman and Inester in 2010. So an essential part of this particular code is that the measured magnetogram is taken and then some pre-processing is applied to make it compatible with force field, because the usual vector magnetogram that we get from measurement, that does not satisfy the condition j cross b equal to 0. So some pre-processing procedures are applied, and that has an effect on the magnetic structures that we visualize for the solar atmosphere. And I will talk more about these effects in the results of my work. Then the second is this. Then the second part is this j cross b not equal to 0, which if we look at the bottom boundary, which if we look at the photosphere, then the plasma beta is much greater than 1, basically. So that tells us that in this momentum balance equation, grad b term is not negligible to j cross b, from which we can essentially see that j cross b is not equal to 0. So that gives us the non-force free model. And in my work, I have used this particular model developed by Bhattacharya and Janki. So when we have these extrapolated magnetic fields of the in the solar atmosphere, then we can proceed to carry out the numerical simulations. So for my work, the model that we have used is the ULEG MHD model. And the basic set of equations involved in this model are as follows. The first one is the momentum balance equation, where the left-hand side term is basically dV by dt. The right-hand side is pressure gradient, then Lorentz force, and the viscous relaxation rate. And the second equation is the magnetic induction equation, where you can see that there is no diffusion term present here. And diffusion term is what I have said accounts for magnetic reconnection. So in ULEG model, there is a property which is called implicit large eddy simulation. So what it does is that wherever we find reconnection sites in say extrapolated magnetic fields, so there it mimics magnetic reconnection, but all the other locations it preserves the condition of flux freezing or maintains ideal MHD. Therefore, it is particularly suitable to carry out the database simulations of solar transients, where reconnection is responsible for releasing the magnetic energy and changing the connectivity. So an effective implementation of this particular code can be written as del B by del T equals to curl of V cross B plus dB, where dB is some numerical diffusion term, which accounts for magnetic reconnection in the simulation. So the code was developed by smaller qubits, and a recent version of the code description can be found in this particular paper. So up till now, this is the basic introduction of what will be required to discuss the results of my work. So what we can immediately see here is that there are two kinds of models, NLFF and non-force free field. And one would like to ask that which model should I use for my study of solar transients? Then, and since these extrapolated fields can be used as initial condition in the MHD simulation, then we need to ask the question that can I employ any arbitrary initial condition for the simulation, or which model should I use? So to address this kind of question, one of the works that was carried out in my PhD was to look at the effect of extrapolated magnetic fields or the initial conditions in a database simulation. So basically, we used the two models, non-force free and nonlinear force free models. And using these two models, we generated three different initial conditions for the simulations. And the simulations were aimed to explore examine the similarities and differences between the simulations. So basically, these are the details of the active region and the flare that was chosen, and this start and peak time. So in this is evolution of this flare, we identified four different brightnings at different points of time, which are labeled as B1, B2, B3, and a B4. And the most important part was the identification of a lasso kind of a structure in the overall evolution of the flare. So a lasso here is shown as lasso is technically a terminology derived from the rope which is used to tame the animals. So that kind of lasso is drawn over here to give a clear picture. So then we carried out the magnetic field extrapolation. So the basic algorithm is to take the vector magnetogram, carry out the extrapolations, and then since we are using this in terms of the initial conditions, we wanted to look at how different are these two fields from each other. And for that, we did a quantitative and a morphological comparison. Morphological meaning that the magnetic structures that we obtain in using both the fields. So in morphological comparison, we obtained a null point and a hyperbolic clustering, which was found to be present in both the models. And we looked at how these structures are similar or different from each other. So in this talk, I am presenting the results of this null point configuration. For this quantitative comparison, what we did was to calculate the angle between the two vectors, which is straightforward, cos inverse of this dot product and divided by their magnitudes. And then we also estimated a difference metric between the two extrapolated magnetic field vectors to look at the differences. And we also compared the extrapolated bottom boundary with the observed vector magnetogram to see how much is the agreement between the two. So one thing is that we found that for non-force free, the average angle between J and B is 65.83 degrees, which is expected because J cross B is definitely not equal to 0 for the non-force free model. And in nonlinear force-free model, the average angle was found to be 8.58 degrees. And generally, it is expected that if the angle is less than 10 degrees, then it is a reasonable, it is a good quality extrapolation. And then we calculated these Pearson correlation coefficients for the vector magnetogram and the extrapolated bottom boundary, and for both the transverse component RT and the vertical magnetic field. So for non-force field, we found the value to be much higher than the NLFF in both the cases, slightly higher. For angle estimation, we found that in approximately 80% of the computational domain, the angle is much less than 40 degrees. And approximately 99.9% of the domain, the difference matrix is less than 10, while the maximum value is 500. So this gave an impression that quantitatively the fields are not too different from are not very different from each other. And then for a morphological comparison, uh, yes, so for a morphological comparison, we looked at magnetic fields on a global scale and local scales. So for global scale, the left-hand figure shows these magnetic field lines in yellow and red colors, which maps the lasso structure. And these structures look to be approximately similar. And for the local analysis, we found a magnetic null point on the top of threatening B3. And in both the models, we detected a null point, but the configurations are slightly different. And importantly, both these magnetic null point configurations uh, are dome-shaped null point configuration. So what's important here is that in the non-force free case, so here a representative vector magnetogram cutout is shown where these positive polarities P1, P2, P3 close in on the inner negative polarity N1, and the rest of the magnetic field line go upward from P1, P2, and P3. So this constitutes the null point configuration in case of non-force free. However, in nonlinear force free, we found that there is no connectivity from this P1, here referred to as primed variables for NLFF. We find that there is no magnetic field connection from P1 prime to N1 prime, while rest of the things are quite similar. So this could be an effect of the pre-processing of the magnetogram, which has completely wiped out one of the connectivities from one positive polarity to the other. But so here one can say that magnetic configurations are not similar, but not exactly equal. Or they are similar, but not exactly equal to each other. So with this, we proceeded to carry out the MHD simulations. And as I mentioned that we carried out 3 simulations. So the first simulation was just entirely using the non-force field. Since its Lorentz force is not equal to 0, it can drive plasma dynamics itself. The second field is nonlinear force field, where analytically the Lorentz force is equal to 0, but in a numerical implementation, there are always some residual Lorentz force, which can drive the plasma dynamics. In the third case, we used the nonlinear force free field again, but supplemented it with a perturbative flow, which is very small, to construct the third initial condition. Then we carried out all these 3 simulations and we wanted to look at their effect on the magnetic reconnection, because essentially reconnection is the one which is driving these transient activities. So the first plot that we constructed is the energy plots, where in the first panel one can see that the decrease of magnetic energy is nearly similar. They are parallel to each other essentially. And while the kinetic energy plots are quite different from each other. So the S1 plot, which has the maximum Lorentz driving Lorentz force, has not reached the saturation and is still increasing. While in the case of the other 2 simulations, the kinetic energy reaches a peak and then due to viscous relaxation, it is decreasing and reaching a saturation value. So the kinetic energy plot can be seen to depend on the Lorentz force, but the magnetic energy dissipation, which is a consequence of reconnection, is nearly similar. So here, if we calculated the percentage dissipation. So, and we found the numbers to be nearly equal to each other, which is approximately near to 5%. So this suggests that all these 3 initial conditions are giving the similar result as far as energetics is considered. Energetics is taken into account. And if we then look at the changes in magnetic field line connectivity, which I'm showing here for the magnetic null point case. So the left column shows snapshots from the evolution of magnetic null point for the simulation S1. And the right, in this right panel, 3 animations are shown corresponding to the 3 simulations. So what's important here is that we found that the first instance of reconnection in this simulation occurs at t equal to 270 in simulation time, and which is quite near to the starting time of the flare thing. And then we found that this red field lines and the white field lines are exhibiting slippage reconnection, which also correlates with the observation of the brightening V3. And then as soon as the simulation proceeds, we find that at t equal to 5 minutes, the lower spine is lost at nearly the peak time of the flare. And if we compare these findings with the other two simulations, then the similar kind of reconnection occurs, but at different times at 180 and 150 in S2 and S3. And lower spine is also lost at 530 and 510. So basically it tells us although the time scale of these events is different, but the essential thing, which is the loss of lower spine or slipping reconnection, so those are nearly similar. Those are similar across all the simulations. So, and if we try to look at the connectivity before reconnection and after reconnection, then in S1, initially all the field lines P1, P2 emerging from P2, P1, P2, P3 are directed towards N1, and now after reconnection they are open. And in S2 and S3, since there was no P1 prime, which contributed to the connectivity, initially they were connected to N1 prime, but now they are open. So this tells us that field line changes in the field line connectivity are also quite similar across the three simulations. And the last and the most important finding of this work is that we can see that in extrapolated field we have a magnetic null point, and we can look at the changes in connectivity at that particular point. But what's most interesting is that spontaneously a null point is generated in the simulation and it disappears in the simulation. So which was not present in the extrapolated magnetic field. So this null point was found to be generated near the location of the hyperbolic flux tube. In the left column, snapshots from the simulation S1 is shown, where at t equal to 0 there is no null point. Then at t equal to 110 we detect a magnetic null point, and then at t equal to 160 it disappears. And similarly, this null point appears in the other two simulations also at different time steps. And it disappears also at different time steps. So the time scale of this null appearance and null disappearance is different in the three simulations. But the important fact is, even though they start from quite different initial conditions, the null point is still generating. And from the perspective of observation relevance, the fan plane of this particular null point was found to the fan plane of this null point configuration was found to undergo slipping reconnection over the brightening B4. So here in this panel B on the right hand side, you can see that the field lines have moved towards the left, but the plasma flow vectors in the black are shown are towards the right, which again connects back to what I said that flipping of the field lines, if they are not in the direction of the plasma flow, can be used to identify magnetic reconnection. So this kind of reconnection occurs across all the simulations, and one can say that these transient structures, which are not apparent in extrapolated fields, can also contribute to the observed observations. So, a conclusion of this work is that the extrapolated magnetic fields are nearly similar, and the amount of dissipated energy across the simulation is similar. Changes in field line connections are similar, and a null point generates spontaneously and disappears. However, the differences are that kinetic energy evolution is dependent on the initial Lorentz force, and the time scale at which these reconnection events are occurring in null point topology are also different. And the time at which this transient null appears and disappears are different from each other. So there are similarities and as well as there are these differences due to the strength of the initial driving Lorentz force. And then there is the result that this transient null can, or the transient structures can also contribute to the observed brightness. So these similarities in simulation suggest something very fundamental, which I will now come to, which I stated in the first slide. In the first slide, that there is something more fundamental to this, to aspects of reconnection other than the energy changing the field line connectivity. So this fundamental aspect is basically called self-organization, magnetic relaxation. So to understand what it all means is that in the context of the similarities that we have seen in the results of the first work is that if we consider an initial state, so here plus and minus are representing ions and electrons to show that it represents a plasma configuration. So basically this initial state one can think of as that before the flare, there is some magnetic configuration. And then there is evolution in accordance with the MHD equations. And then we arrive at some final state, which is different from the initial state. So this state will definitely have lesser energy because magnetic energy is lost in the flare. So this kind of process where where we have in some initial magnetic configuration with higher energy, and we go to some lower state to a state which has lower magnetic energy, can be thought of as a relaxation of the magnetofluid. So relaxation meaning energy is getting lower. So this brings in the perspective of what is known as self-organization. So what self-organization means is that this final state, which is shown here, exhibits some form of long-range order in a quantity. So this long-range order can be, this is the technical definition, but it can be understood that these coronal loops, these are large-scale structures or large-scale magnetic flux rods. These are highly ordered magnetic structures. And so why do they form in the first place? Why do they need to be so much organized? Right. So this is the context of long range ordering. And, but this long range ordering during this, when this initial state is going to final state, is accompanied by a short range disorder. So the short range disorder can be understood as reconnection at these small scales. So a principal result of self-organization is that the final state is nearly independent of the initial state. So it states that whatever initial condition you start with, you will end up with a nearly similar final state. And a more relevant example of illustrating this statement is that there are different types of galaxies, spiral, many other shapes. So the ultimate outcome is you have a galaxy, irrespective of what its shape is. So that galaxy can also be considered as a self-organized structure. Maybe there can be large scale loops, small scale loops, but ultimately they are all loops. So there is some kind of independence in the final state, which is generating all these structures. So in presence of dissipation, because we are talking about short range disorder, and which is ultimately reconnection at small length scales. So these quantity A and B, they decay at different rates. So, and because they are decaying at different rates, this can be used to formulate a variational principle where the quantity which is decaying the fastest is used as a minimizer, and the quantity which is decaying slowly can be used as an invariant. So the quantity which is decaying slowly, the quantity B, sorry, I said it inverse, the quantity which is decaying slowly is always associated with long range order, which is the quantity A. And the quantity which is decaying the fastest is always associated with short range with disorder, the quantity B. So a very relevant example of such formulation is magnetic relaxation, where this magnetic helicity defined as integral of A dot B dV is considered a constraint. So if we take a time derivative of this helicity, then what we obtain is that dH by dt is minus 2 times integral eta j dot p dv. And if we take the time derivative of magnetic energy, it is minus eta j square dv. Then if we estimate these, if we make an order of magnitude estimate of these terms, we end up with the following. Because current is curl of B, then we have B by L. And then if we take J dot B, then it is approximately equal to B square by L. So this J dot B is in the helicity term. And it is much less than J square because J square is proportional to B square by L square, and L is a small length scale. So this term ends up being higher. Therefore, this tells us this decay of magnetic energy is much larger. The rate at which magnetic energy decays is much higher than the rate at which helicity is decaying. So this gives us this connection between the quantities A and B, where this short range disorder is due to a release of magnetic energy in the eruptive events, where magnetic energy decays faster, while this long range order is because of helicity, because its decay is much more slower. So if we make a formulation of this in the variational principle, and we define a functional F, which minimizes magnetic energy B square, and with a constraint that helicity is nearly invariant. Then finally one ends up in the final state, or which is given by curl of V equal to alpha B. From here one can see that this represents a linear force free field. So therefore, this fundamental principle of self-organization and magnetic relaxation is already giving us this connection of the with the extrapolated magnetic field, which we encountered previously. So in the previous work, we found that okay, we are getting near similarity in the results. Therefore, the results of reconnection are exhibiting the signatures of self-organization. So we can take a step ahead and explore magnetic relaxation and see if we start with with the extrapolated magnetic field for a flare and do a simulation, what kind of state do we get? Do we get a linear force free field, which is shown here as curl of V equals to alpha V, or we get some other kind of state? So for this, here is the second work which I carried out in my PhD. So basically, we selected a flare whose movies are shown here in 304 and 1600 extrom channel. And so in this case, in this flare also the workflow remains the same. We identify the brightness P1 and B2 at the beginning of the flare and the peak time of the flare. And then 304 angstrom channel, we recognize the dome-shaped kind of structure and chromospheric flare ribbons. So we make some contours on this dome-shaped structure to verify that it looks like a dome-shaped structure. And then if we carry out the magnetic field extrapolation of this particular region, then what we found is that there exists a hyperbolic flux tube, which is shown here for context in the left-hand side panel. So here you can see that there is a blue field line, there is a red field line, and then there is a yellow field line and there is a pink field line. So this uh, blue and red can be thought of as one QSL, and this yellow and pink field line can be thought of as constituting another QSL. The colors are chosen here with respect to the extrapolated field configuration. So here you can see that this mapping of this Q factor, which tells us how much is the gradient between the field lines mapping. So this shows a characteristic X kind of shape, which confirms the interpretation that this is the hyperbolic flux tube. And then also with respect to the observation, we found that the part of the HFT constitutes a dome-shaped structure. So the match between the extrapolated magnetic field and observation is quite well, which gives us the motivation to carry out the simulation. So one of the there are two aspects here for we say that magnetic energy is decreasing during the flare. So I thought that in a simulation or in a numerical approach, what kind of volume do I need to take to say that really magnetic energy is decreasing? And the second is that in the previous slide, where we obtained a linear force field as a consequence of self-organization. That theory was given by Taylor, and he considered that the entire volume is perfectly conducting. The surface of the volume is perfectly conducting. But solar corona is an open system, and therefore we cannot have any such volume. So if I want to study relaxation and if I want to see from where energy is actually getting decreased in the case of flare, then what kind of what kind of volume do I need to choose? So for that purpose, we selected three different subvolumes, and basically we tried to analyze how the energy, what is the dynamics which is governing the evolution of magnetic energy. So here once again, this induction equation within the context of Euler MHD model is given as curl of V cross V plus this numerical figure, and magnetic energy is integral V square dV. So if we take its time derivative and use this equation del V by del T, we end up with this kind of equation. So basically, the first term tells us that which is the work done against the Lorentz force. So this term can basically increase the magnetic energy or decrease the magnetic energy. So this represents the conversion of magnetic energy to kinetic energy. And the second term is essentially Poynting flux, E cross B, where E we have taken here E ideal because in Euler MHD the induction equation is del P by del T equals to curl of V cross P without diffusion, and we can obtain E ideal very easily using the values of velocity and magnetic field. The last term is entirely due to the diffusion, and which goes to the dissipation of magnetic energy. So this Poynting flux is relevant because if we choose certain subvolumes, energy can come into the subvolumes or go outside. So which can change the magnetic energy profiles. So basic idea is that magnetic energy can change due to the work done by Lorentz force, Poynting flux, and dissipation. So for this analysis, we chose three different subvolumes, which is shown here is S1, S2, and S3. So this subvolume S1 we chose so that it is centered on the X region of the HFT. And S2 subvolume is chosen so that it covers the entire HFT configuration. And S3 is chosen so that it covers the entirely observed brightenings. And these arrows along the Z direction, the length of these arrows along the Z direction are in proportional to their size along the vertical direction. So basically in all these volumes, we evaluate the volume averaged magnetic energy, volume averaged current density, volume averaged twist, which is given by J dot B by B square, and gradients, because J by B parameter is essentially curl of B divided by B, and so that B cancels out and curl is representative of length scale inverse, which tells us how much is the gradient in the magnetic field, and gradient is essential for seeing that where small scales can get generated and cause reconnection. So basically in all these three subvolumes, for all these three subvolumes, here I'm showing the evolution of magnetic energy, twist, and magnetic field gradient. So what's important here is that uh, in subvolume S1, which is centered on the exponent of HFT, initially I thought was that since reconnection is occurring at that particular X region, energy should decrease. But what we found is that initially energy is increasing, then it is decreasing. This was the one question that why it is happening. And the twist and gradients have decreased in all the three subvolumes overall, but the magnetic energy profile was not, we were not able to understand quite well. So for that, we essentially carried out the estimation of Poynting flux. So I'll present those results here. So in subvolume S1, we see, or even though the fielding connectivity is changing, but the magnetic energy increases and decreases, while the other two parameters are decreasing, which is consistent with the expectation of that reconnection is going to make the field lines more simpler, so that it will decrease the twist and reduce the gradients. And in the subvolume S2 again, initially the magnetic energy decreases, but then it starts to increase. That is also the question why. So, and in this case also twist and gradients are decreasing. While in the third case, we observe that magnetic energy decreases almost continuously. Uh, in this case, twist and gradients increase towards the end of simulation, and the reasoning was question was fine. So for the last this question, that the increase of twist and gradients in this larger subvolume, we found that at the top of the computational box, there is a converging flow which is increasing the gradient and hence the twist of the magnetic field. But more important was the evolution of magnetic energy in the three subvolumes. So from here itself, one can see that if we consider a large subvolume, then only I'm able to get that magnetic energy is decreasing. While if I have a smaller subvolume, then I'm not able to say that a flare is that the flare must exhibit a decrease of energy. So that when we are doing things numerically, we have to be certain of what kind of subvolume we need to take to show that really magnetic energy is decreasing. So for that estimation of Poynting flux uh, and the numerical diffusion. So here what is done is that we have calculated Poynting flux and calculated the numerical diffusion, because this estimation of Poynting flux is based on an ideal. Yes, somebody has raised a hand.
Uh, Hi, Satyam. I
Yes.
want to ask you, so the choice of this volumes, is it artificial or you have some intuition to take that volumes?
Yes. So the intuition is that because there is no guideline to selecting these subvolumes. So I thought what what I can use, what information I can use to select this subvolume. So the first one was definitely this X region of the HFT where reconnection is occurring. So I thought I should make a subvolume which is which is very tight and encloses the X region. The second was that, okay, I have this HFT configuration which has some spatial extent. So I can take a subvolume which encloses this entire reconnection morphology. And the third, the larger subvolume is to see because the brightening is spatially extended over a larger region. So then the intuition was to say that, okay, I can take this entire brightening into account to select another subvolume.
Okay. So the relaxation rate or the relaxation timing, that is more kind of local rather than the global perspective that you are analyzing. Is that so? Or
Relaxation rate.
the relaxation time scale or the relaxation rate that you are estimating by different zones and by selecting different domains. So, I mean, the more exact statement will be the relaxation is localized.
Yes, that will end up in, as you are right, that will end up in a conclusion because this reconnection is localized kind of. So relaxation in that context of reconnection, because it is localized, one can say relaxation is occurring locally because reconnection is occurring at a particular point. But always for a relax, because we always need to consider a global picture because the decrease of magnetic energy is what is central to relaxation. But that decrease of magnetic energy I'm getting only when I consider a larger subvolume. So that in that simulation, the energy will not decrease only because of reconnection. It will also get converted into kinetic energy because of V dot J cross P. And that kinetic energy will be ultimately lost as due to viscous relaxation in the system. And the second aspect is because this is the primary reconnection site in the HFT. But there can be other reconnection sites as well, which are present in the subvolume S3, which might be contributing to more reconnection and therefore dissipating more energy. So yes, so that is my idea. I'm not sure if I have answered your question or understood.
I mean, I mean, partly I'll say, but okay. I mean, I have some idea what you are saying. But is that the relaxation? How much it is sensitive to the outflow of your material from the box? I mean, do you have an open boundary at the top or?
So for all these subvolumes are within the computational domain. So for the subvolumes, all the boundaries can be considered as open.
Yeah,
And
but if
for
you
the
take the,
yes,
sorry. Yeah, if you take the full box, the
yes,
full domain.
even on the full box, we impose open boundary, and so that the flux is essentially constant through the outer boundaries of the computational box.
Okay.
So these open boundaries will contribute to the pointing flux. That is why pointing flux is relevant. That even if reconnection occurs inside some subvolume, and there is some kind of flow, either from inside the subvolume to outside or from outside to inside, that can advect field lines inside the subvolume, or it can twist also the field line. It can also twist the field lines. So where comes the contribution of pointing flux in governing these magnetic energy changes when my subvolumes are smaller?
Okay. Thanks. Okay.
Okay. So to understand these magnetic energy changes in the subvolumes, we calculated Poynting flux. And since this Poynting flux estimation is only based on the ideal electric field, because we do not have a physical resistivity in the simulation, and therefore we cannot entirely calculate all the complete Poynting flux. So we also estimated this diffusion, numerical diffusion, an approximate estimation by calculating del B by del T minus curl of V cross. So to see actually where diffusion is dominant and whether we can apply this Poynting flux estimation or not, because this is based on the condition that ideal MHD is satisfied. So what we obtain is the following. So first, if we look at the top three figures, this magnetic energy is increasing then decreasing. And in this central panel, I have plotted this parameter D. So this D has a high value around 0.09 around the X region of the HFT, which is shown in blue color. But if we go away from the this particular region, this D value is decreasing, mostly in the green colors. So which is consistent with the ILES property of the ILES property of the simulation also, that only where there are strong gradients or where their reconnection is supposed to occur, this numerical diffusion has a high value. And then if we look at the Poynting flux variation of the Poynting flux, then we have to keep in mind that when Poynting flux is positive, that is S is equal to E cross B is positive, then it means energy is going outside the system. But when it is negative, then it means that energy is coming inside the system. So if we look at this profile of this Poynting flux, we see that initially it is positive, which means energy is going outside the system, but it doesn't agree with the profile of magnetic energy, which shows an increase in magnetic energy. Then in the later parts, it is showing a negative value, which is kind of in agreement that magnetic energy should increase. Then even after here also, that when the value becomes positive after the red dashed line, then it shows the energy should decrease, which is again consistent with this phase P15, where energy is showing to be decreased. So in this subvolume S1, we see that the variation of Poynting flux is in agreement, but does not completely agree with the profile in certain phases like P12, where it is positive, showing outflow of energy, but actually we are seeing an increase in energy. So, so basically we can say that this could be possible because the diffusion is higher at certain places, so that this estimation is not entirely accurate to describe the variation of magnetic energy in subvolume at every time instant. And since the diffusion has a high value, it says that diffusion is localized in S1, where the X region of the HFT is situated. And if we look in S2, we find a better agreement that if in S2, if we look at the values of diffusion, so the highest value of diffusion is much less than what is observed in the subvolume S1. And if we look at the first phase of the Poynting flux, which is positive, which suggests that energy should decrease. And in the later phases, it is always negative, which suggests that energy should increase. Therefore, when we are increasing the size of the subvolume, and since my diffusion is always is mostly localized in S1, then therefore this Poynting flux estimation is more accurate for the subvolume S2. And it also explains the magnetic energy profile in this subvolume. And illustration of this, that Poynting flux is actually dumping energy in this subvolume S2 is shown by this animation, which shows that initially some part of the green field lines is lying outside the box, but with time they are entering inside the subvolume, which shows that flux tubes are getting advected inside the subvolume, therefore increasing its energy. And if we go to the subvolume S3, the diffusion value reduces sharp by 1 to 2 orders of magnitude, and which implies that diffusion is localized in S1. And since Poynting flux, here you will see that Poynting flux is mostly negative for most of the part, which suggests that the energy should increase. But since the order of the Poynting flux is 0.03 as compared to 0.6 in S2, it is almost 30% less, which we estimated. Therefore, in subvolume S3, which is the largest subvolume, the Poynting flux itself is very small. Therefore, its sign does not matter. And the energy decrease in S3 is primarily governed by magnetic reconnection. So if we take a large enough subvolume, then we can finally numerically arrive at this conclusion that magnetic energy is actually decreasing. But if we take smaller subvolumes, then the Poynting flux will definitely play a role in governing the energy profiles in those cases. And the last result of this work was to estimate the extent of the magnetic relaxation, where we have this linear force free field curl of B equals to alpha B. So it is J equal to alpha B. So if we wanted to, so basically we wanted to test how much the relaxation has occurred. So for that, we calculated the angle between current density and magnetic field. Because if we would have reached a linear force free state, then essentially theta would have been very small, maybe say analytically 0 degrees, then that would correspond to a linear force free field. But numerically also the value should have been less, 4 degrees, 5 degrees, less than 10 degrees, whatever. So basically then we check the distribution of current density and magnetic, the distribution of theta between current density and magnetic field in all the subvolumes at the initial time of the simulation, at the end time of simulation. So in subvolume S1, I could not identify any clear pattern because the size of the subvolume is very small and therefore the number of voxels are very limited. But in S2 and S3, there is a clear-cut result that the blue line, which is at the initial time of the simulation, is showing that a large percentage of the voxels have values around 75 degrees. But at the end of the simulation, these values have decreased and the values around 15 to 30 degree has increased, which shows the angles have definitely reduced. And similar result is found for the subvolume S3. So it shows that as a consequence of reconnection and the magnetofluid dynamics, the current density is becoming more aligned with magnetic field. But how much is the extent? So when we integrated over the whole domain, that we found that the angle changes only by 4.3 degrees, and the final average angle is only 60.01 degrees. While for the case of force free, even if we take a nonlinear force free for reference, the angle, if we would have obtained the 60.01 degree to be within 10 degrees, then one could have said that there is a approach towards the linear force free state. But we find that the terminal state of simulation is not in a force free state, and therefore we have not achieved any equilibrium in force, and further relaxation is still possible. So as a continuation of this study, I am not presenting here. So what we concluded from this study was there might be a possibility that since flares are of different strength, they may have a bearing on the extent of relaxation or how much relaxation is going to finally occur. So that I carried out in a different study. So here the conclusion of this study is that we find an HFT which is nearly co-spatial with the brightening, and we analyze the evolution of this current magnetic energy, current density, twist and gradients to explore the dynamics of different subvolumes. And then we investigated Poynting flux and numerical diffusion to understand the dynamics, and also explored the evolution of angle between current density and magnetic field. So for the energetics, what we found is that diffusion is mostly localized in S1, which is kind of expected, and that the largest subvolume, the energy profile of the subvolume S3, which is the largest, is governed by the localized diffusion in S1 and slipping reconnections in S2. Therefore, the consequence of reconnection, which is to decrease the magnetic energy, is only manifested completely. The expectation is manifested only when the subvolume is large enough, so that the Poynting flux is not playing around with to change the profile. So, and for the relaxation aspect, we find that in the previous study also we find that there are signatures of self-organization, and in the simulation we find that there are signature of relaxation because angle is decreasing. So therefore it tends towards a force-free state, but the relaxation is not complete. Therefore further relaxation is possible, and therefore we thought that if we look at different strength flares, then we can study more about the extent of relaxation. So the broad summary and conclusion of my entire talk is that flares are manifestations of reconnection, and reconnection is associated with these changes in energy, magnetic energy, change in field line connection, self-organization, and relaxation. So to explore these aspects, we looked at these database simulations where we use extrapolated magnetic field as an initial condition. And the broad conclusion is that both NFF and NLFFF extrapolation models can be actually used for database simulation because the consequences of reconnection remain the same, although time scale might be different. And that simulations show signatures of self-organization, but the terminal state we do not found it to be reaching a force-free state. So the overall objective has been always to learn more about these eruptive events, solar flares, and from a fundamental point, if we can gain more information by studying self-organization and relaxation. So yeah, so that's the end of my talk. And Argadi, please let me know what to do,
Yes.
what needs to be
So
done.
Does anyone have any questions? Anyone have any questions? If yes, then please feel free to unmute yourself and ask.
Yes, Satyam, I have one question. First of all, excellent talk. I enjoyed the entire session. And I have one question. So regarding the non-force free initial state as your extrapolation, so what would be the relaxation rate for a high initial Lorentz force and low initial Lorentz force? I mean, in which case it will be faster?
So I'll go to the result. So in this case, when we did three simulations using this both non-force free and non-linear force free field, right? So for in each of these cases, we find that the amount of energy dissipation is although similar, but the scale over which it might occur could be different. So can you elaborate more on what you mean by like relaxation rate?
Okay, so in figure 4,
Yes.
so the rate of decrease of the magnetic energy. I mean, if you take a time derivative of your
Right.
magnetic energy, so in which case the rate will be higher for high Lorentz force or low Lorentz?
In these results, what I found is that if since these curves are almost parallel, so even if I take a time derivative, that would be almost equivalent.
Okay, okay. So, so it doesn't depend on the initial Lorentz force value.
So yes, I mean for this set of initial conditions, one cannot. I think there is this needs to be mentioned that we cannot always choose any arbitrary initial condition and say that these results are independent of the initial condition. So if I take a potential field, I may not find the comparable structures like null point and HFT in these two cases. So the initial conditions are not completely arbitrary. And since these extrapolated magnetic fields are quite similar, when I compared these different extrapolated magnetic fields, they were quite similar. So that could be the reason of this near parallel nature of these curves. The important part was that in an NLFF implementation, analytically the force is zero. So we do not know whether the residual numerical force, how physical it is, but still it is giving similar result. So this time derivative would be nearly same because the curves are almost parallel.
So this is actually bit differing with the result. But okay, we can discuss after the meeting if you are interested.
Yes, sure.
I can show you something.
Okay, so how will you contact me? WhatsApp?
I can send you an email.
Okay, cool.
Okay, so I see there is a message in the chat. So Satyam, can you see the chat? If you can, then would you like to answer it?
Okay.
He asks where can he get the code for the nonlinear force-free field?
Okay, so for nonlinear force free, what I know is that there are multiple codes for nonlinear force free extrapolation in general. So for the open codes are one of the NLFF codes is on the GitHub repository by Yang Guo, which is an open source NLFF code. The NLFF code that I am using is from Wigelmann's group. So that code is not open. So one has to request Wigelmann for the NLFF code. And I can find other open NLFF codes also because there are different algorithms also to implement NLFF, if you are interested.
Okay, are there any more questions from anyone? Okay, if not, I would like to thank Satyam once again on behalf of everyone. Thank you, Satyam, for this wonderful talk. And we'll see you all again. Yeah, we'll see you all again in the next seminar then. Wait a minute. So there is a follow-up with from Mayank. He says that the other thing I have used VCA NLFFF. How is it different from the normal NLFFF?
The VCA and NLFF is I think by the Ashwandan, and right now I do not recall what he does in the code, although I've used it 3-4 years back. So maybe I need to look into it how it is different from the normal NLFF version.
Okay, yeah, he has some technical difficulties, so maybe you can email Satyam if you have any further questions as a follow-up.
So I can write in the chat box.
Yeah.
Oh, I think this message went to someone else. Can I agree?
Yeah, we got your email on the chat. Okay, so thank you, Satyam, for the talk, and yeah, we'll see you all again in the seminar. Have a good day.
So I can leave the meeting.
Yes.